Okay, so start now. I'm audible, right?
Yes, sir.
Okay. So, what we will discuss today. So, this is live session 5, and we will go through few topics like mm, we will go through few topics like adhesive joining. Then we have some solid state joining techniques, and in solid state joining techniques, you have different techniques like ultrasonic, friction stir. Then you have diffusion journey. Okay? So we'll go through these things one by one. So today's session will be mainly on theory aspect. Uh, the numerical part is less over here for today's session. Anyhow, so let's start from adhesive joining. So in adhesive joining, what do you use as an adhesive is a non-metallic material, right? So the adhesive will be a non-metallic material. Adhesive will be a non-metallic material, and that basically will fill your gap and create a joint between your two surfaces, right? So the actual adhesive span a wide range of material types and forms. So it can be some thermoplastic resin, it can be some thermostatic resin, it can be some artificial elastomer, and even also some ceramics also can be used as your adhesive material. And how they should be applied, they can be applied, it's simply you can think it of as a glue kind of thing. So they can be applied as drops, as tape, as coatings. So as different forms of things, they can be applied in between two metal sheets to join, right? So yeah, adhesives also adhesives also are available in the form of liquids, gels, even solids, right? Now, what is the fundamental thing in adhesive is curing. So curing is the fundamental aspect in any kind of adhesive process. So what do you do in curing? So curing is basically you are inducing some kind of heat or radiation or light or some kind of activators, right? So uh, that kind of thing you are basically, if it is in a molten state, you're thermosetting or thermoplastic polymer. By curing, you are basically solidifying that, right? Now, what could be the applications for adhesive joints? It can be structural adhesives, it can be some light duty for fixturing purpose, it can be some simply sealing aspect, right? So it can be uh, forming of liquid or gas type joints, right? So if we see in terms of applications, there can be. structural adhesive. There can be light duty or fixturing kind of for fixturing purpose. And then finally you can have some sealing of joints. Right? Now, structural adhesives are mainly selected for their ability to transmit your load effectively, right? So it can include some kind of epoxies, it can be some anaerobics, it can be some acrylics, urethanes, silicones. These are different kinds of adhesives which are mainly used for structural purpose, right? So I will note it down. So you will have. So let me take another slide. So for structural adhesive, what do you have? You have epoxy, you have something called cyanoacrylics. Cyanoacrylics or acrylates. Then you have anaerobics. Then you have acrylic, silicones. These are different adhesives which are commonly used in industry. Um, so we'll go through one by one. If you see epoxies, epoxies mainly are used over a temperature range from, so the temperature range is very wide in nature, right? It can act from somewhere around minus 50 to 250 degrees C. This is the temperature range in which epoxy can be used, right? And after curing at room temperature, the shear strength what you will achieve will be very high. So it can be somewhere around uh, 30 to 100 megapascal. These are some uh, rough values which I am mentioning over here. It depends on how much epoxy you are using over there. And then in terms of epoxies, there can be single component epoxies. There can be two component epoxies, right? Mainly what is common in use is two component epoxies. What is two component epoxies? So you will mix up a resin and a curing agent over there, and also you can mix up some additives, some accelerators, some plasticizers, some fillers that will basically enhance your curing rate, that will enhance your flexibility of the adhesive, that will enhance your kill resistance. So yeah, so I will call it as two component epoxies where with the epoxy we'll mix up some resin as a binder. We'll mix up some curing agent also to enhance your curing rate. Okay. Then if you see this cyanoacrylates are also commonly known as super glue. So these cyanoacrylates are also known as super glue. So what do they do? This super glue material, these are mainly liquid monomers, right? So this liquid monomers that will polymerize when sprayed into a thin film between two surfaces. So this super glue material are mainly liquid monomers which can polymerize when sprayed into a thin film between two surfaces. Okay. Now this family of adhesive, they are available in the form of liquids and also in form of gels with varying viscosity. It can be toughened version designed to overcome some brittleness and even some uh, non-frosting varieties, right? Then if you see this anaerobics material, so we talk about epoxy, we talk about this superglue material. Then if we talk about this anaerobic materials, this is a one component thermosetting acrylics, which will remain in liquid when it is exposed to air. Okay. So if we talk about anaerobics, so this is all information based thing, right? So you have to memorize these things. Um, this is a thermosetting polyester acrylics. It will remain in liquid when exposed to air, right? Now, when it is confined to a small space and if you shut it off from oxygen, as in a joint to be bonded, so the polymer will become unstable. Okay. Now, in the presence of iron or copper, am I audible?
Yes, sir.
Yeah. Okay. Now, in the presence of iron or copper, uh, it will polymerize into a bonding type resin. Okay, without the need for elevated temperature. So, in the wait for some time. I have disconnected from my tab. It's raining over here, and I think the Wi-Fi is not working properly. Let me check once. Huh?
Okay, sir.
Is the screen visible now? Is the screen visible now?
Yes, sir.
Yeah. Great. So,
Yes, sir.
yeah, thanks. So, we were talking about anaerobics, right? Now, I was talking about this anaerobics when it will be confined in a small space, and if you cut down your oxygen supply, so because you're basically keeping it in between two metals to be joined, right? So, the polymer will become unstable. Now, these anaerobics are extremely versatile and it can bond almost anything. So, it can also include wily, dirty surfaces also, right? And then you have acrylic materials. What is there in acrylics? So, acrylics, they mostly involve application system where you have some catalyst primer or you have some curing agent which is applied to one of the surfaces to be joined, and you are applying adhesive to the other surface, right? Now, if you apply heat to acrylic mixture, it can often accelerate the curing, uh, the curing process, right? And yeah, the major limitation in acrylic uh, adhesive joint is it will include pore strength at high temperature, it will have flammability, and it will have some kind of odor, right? When it is still uncured. So, if you are thinking of limitations, I will note it down. If you are thinking of limitations of acrylics, they have core strength, they have core strength at high temperature, they are flammable also, and they will have some bad smell when it is uncured, right? Then you have some urethane materials. I'm not going through everything. You'll have some urethane materials, then you'll have silicone. So silicones are basically thermoset polymers, right? So silicones will be thermoset that will cure from the moisture in the air or absorb moisture from the surfaces that are being joined, right? So yeah, you'll also have some high temperature adhesives. So you'll also have some high temperature adhesives for some high temperature application, of course. High temperature, high temperature adhesive. So what the name suggests, at that point of time, your strength must be retained at temperature, right? So mostly this will be excess of some 300 degrees C. So the strength of adhesive joint, strength of joint will be retained at temperature higher than 300 degrees C. Right? So these are your structural adhesives. Now in terms of non-structural non-structural thing, uh, what could be some application for non-structural application? It could be some packaging, some labeling, as I was saying, some sealing purpose to have some gas type joints. There you will have something called hot melt adhesive. So for non-structural application, non-structural Natural application. What adhesive do you have? We have hot melt adhesive. We'll have evaporative adhesive. Then pressure sensitive adhesive. So in evaporative adhesive, uh, we'll use some organic solvent or water base that will be coupled with some acrylics or polyurethane or vinyl, or it can also be mixed with some various types of rubbers. So common evaporative adhesives are uh, rubber cements, floor waxes. These are common evaporative adhesives. So now for pressure sensitive adhesives, no problem, Kumar. So you can you can take the notes. Anyhow, these videos will be uploaded later in YouTube. I will be uploading the this presentation in PDF also. So I think NPTEL will be sharing the link for each and every YouTube video link and the folder where I'm keeping these lecture notes. So that should not be a problem at all. Okay. Anyway, you can take the note and let me know if it is done. Thank you. Okay, so we'll be moving to this pressure sensitive adhesive. So over here, there is no need to cure the things. You will apply little amount of pressure, and what will happen that the bonding will be done completely at room temperature with applying with some brief application of pressure. Right over here, no curing is involved. So that is a pressure sensitive adhesive. Okay. Now, if you think of most of the adhesives, they are electrically and thermally insulating in nature, right? So they cannot conduct heat as well as electricity very well, right? But if you want, you can also prepare some conductive adhesives also. How we can produce some conductive adhesive? You can incorporate some selected fillers such as uh, you can include silver or you can include some conductive materials of good thermal and electrically conducting. Right? So you can include silver or copper or aluminium or nickel or gold in the form of flakes or powders. Okay? So I'm talking about conductive adhesives where you will add feeders of copper or aluminium or nickel, silver in the form of flakes or powders. Okay. Now Yeah. Now, how you should design your joint for a structural adhesive, let's say, because there is such a large difference in bonding area. Adhesive bonded joints are you can classify your adhesive bonded joints in three ways. So I will classify my adhesive bonded joints in three ways in terms of design consideration. Okay, so adhesive bonded joints. Let me take another color. How you can classify them? We will classify them something called continuous surface bond. So over here, both of your adhering surface will be relatively large and are of the same size and shape. Okay. Then you will have core to face. What is happening over here? You will have one adherent area that will be very small compared to the other. So what could be some example? Let's say you were joining some honeycomb core structure with some flat facets. So your honeycomb will look something like this. So something like this with some flat facets. So one of the area is smaller compared to the other metal. So that will be called core to face bonds. Okay. Now your joint your joint can be subjected to tension, compression, shear stress, even some peel stress also, right? So you're familiar with this kind of loading, right? You're familiar with tensile loading, you're familiar with compression loading, you're familiar with shear loading. What is peel? So experimentally, we also call it P peel or U peel, depending on in what configuration you are doing the experiments. It's basically something like this. So let's say this is one of your metal, this is another metal, and I'm having some adhesive like this. So this is my adhesive, and you are peeling it off like this. Okay. Now, most of your structural adhesives, they are significantly weaker in peel stress. Why? Because over here, if you see, the stress will be concentrated on only a very small area of the total bond. Then they will be in shear or tension. So structural adhesives will always be weaker in peel stress compared to tension, compression, or shear. Okay, you can have some creep, some vibration, some fatigue, or some mechanical shock that can also induce some additional stresses, right? Can you name few joint designs like lap joint? You have heard of lap joint, right? You have heard of butt joint. Then there are few more joint designs. You can have some double lap joint. You can have strap joint. So let me, okay, how we should mention it. Let me draw these joint designs. So you can have lap joint. So this is my adhesives, right? You can have, what will be this called? This is called double lap joint. Okay. What will be this called? This is called half lap joint. Okay. There are few more. Um, there are strap joint. There are double strap joint. Now, useful strength is generally obtained by increasing the bond area. As simple as that. So if you are increasing your bond area, will increasing the uh, ability to sustain higher amount of load, right? So to increase your bond area, you can add some straps or the conversion to some form of lab designs what we are talking about over here, double lab, half lab, this kind of thing, right? Now adhesives can also be used. So now I am talking about how you can increase your load sustainability. So how you can increase your load by increasing your bond area through some uh, designing your joint properly. Now, adhesives can also be used in combination with uh, welding, brazing, these kind of joining techniques. So, spot weld or rivets, they can provide you some additional strength, right? They will provide you some additional strength or simply prevent movement of components when the adhesive is not fully cured or it is getting softened by exposure to elevated temperature. So these are some hybrid technique along with adhesive. You can do that. Now, there is something called weld bonding. Are you familiar with this? Weld bonding? Yes or no? At least you must have heard of this term weld bonding. This is there in the video lecture. Uh, Welding and adhesive bonding are two very different methods of joining, right? And they are typically considered uh, to be competing technologies. Now, when they are used together, when they will be used together, that process is called weld bonding, and they're often combined in a way that they will complement. Yes, yes, yes. Spot plus adhesive. Correct. So they will often combine in a way that they will complement one another and cancel each other's negative features, right? So it may not be only resistance spot. Yes. So it can be resistance spot, laser welding, friction stir, ultrasonic welding. All can be combined with adhesives to join some dissimilar metals if it is not possible with only adhesives. Okay, let's say you are joining steel to aluminum. It will be very difficult with only using some adhesives or some. high structural adhesives which can sustain high temperature application. That will not be possible. So you must have uh, include the hybrid aspect over there. So as I was saying, it can be laser welding, it can be friction stir welding, ultrasonic welding, different solid state welding techniques. Right? So yeah, weld bonding is combination of spot welding and adhesive welding. Okay, so this is in brief on this adhesive joining technique. Let's see if there is any question on adhesive joining techniques, and then we will move to this solid state joining technique. Okay. Any question till now? It's raining over here. Any question? I think we have a single question from adhesive. It asks, as compared to spot weld joints, weld bonded joint will offer you high fatigue strength, lower stress concentration, high impact strength, and all of this. Which one should be true? Which one should be true? So when looking at the choices, it must be all of this. If you have any question or confusion, you can ask me. If you don't have, we'll move to solid state welding techniques. Okay. So next we'll move to solid state welding techniques, and first we will cover ultrasonic welding. So what is happening in ultrasonic welding? We will have some localized application of high frequency shear vibration of low amplitude. So you have low amplitude, high frequency vibration. This is the first and foremost principle of ultrasonic welding. How you can the power source of ultrasonic welding. What is the order of frequency? It can be as high as 10 to 200 kilohertz. Okay, so my frequency can be 10 kilohertz, 200 kilohertz, based on your application, based on your joint geometry, what material you want to join, right? And what can be the order of amplitude of the vibration? Usually is less than 100 micron. Okay. Now you have to apply light normal pressure for your parent metals which you want to join during the processing. Now, although there is some heating at the contact interfaces, or we call it fang surface, the interface temperature rarely exceeds half of the melting point of the material. So I'm talking about in an absolute temperature scale. So if you are joining aluminum, let's say aluminum to aluminum, what is melting temperature of aluminum? Any idea?
600 degree approximate.
So it is a little higher than 600. It is somewhere around 660, 670, 680,
Okay, sir.
650. Great. Okay. So in ultrasonic welding, the temperature range what we will be working with, that must not exceed half of its melting temperature. So it should not exceed 300, somewhere around 300. So the working temperature will be somewhere around 200 to 300 degrees C only, right? So how the joining is happening? So it appears that the rapid reversal of stress along the contact interface because of high frequency vibration, it will help the interface to deform, it will help the interface to shear, it will help the interface to flatten the surface asperities and break up and disperse your oxide formation if it is anything there, right? So basically it will remove your surface contaminants if it is some surface roughness is there. With high frequency vibration they will get flattened, so there will be breakage of oxides, there will be small locations where initially joining start, and then over the period you will increase the contact area like this, something like this. Everything is happening at the temperature range of 200 to 300 degrees C only, right? Now what are basic components of ultrasonic welding process? Let me draw a figure, basic schematic. I will not draw a hi-fi drawing. So and draw some basic schematics. So you'll have some mass of your ultrasonic transducer, and you will apply some force over here, and say it is having some column, and this is the work table where you are joining. This is my metals to be joined. This is the table, and you have something called reflected sonotron. Sometimes we call it also anvil. So this is, I am having vibration in this direction. We'll have some ultrasonic transducer. The same what is used in ultrasonic machining process. So yeah, it will have some AC power source. This is ultrasonic transducer, right? So this is a coupled force application system that contains a welding tip on one end, and it can be either stationary for spot welds, or it can be a rotating one for seam welds. Like you see in resistance spot welding also, you'll have a stationary spot welding electrodes or some roller kind of thing for seam welding operation, right? Now over here, the workpieces which need to be welded, that is placed between this tip and a reflecting anvil, as I was saying. And because of that uh, tip, you are basically concentrating the vibratory energy to a relatively small area. So I'm concentrating a vibration energy over a small area, right? Now, ultrasonic welding is restricted to the lap joints only. So mostly you will be doing lap joint of thin metal sheets. It can be thin metal sheets, it can be foil, it can be wires also, correct? What can be the maximum thickness what you can join in ultrasonic welding operation? The maximum thickness what you can do is somewhere around 2.5 mm. So maximum thickness is 2.5 mm. What will happen if you go beyond that thickness? You need to have some high power source. You will have some much higher frequency. Maybe you have to use some higher amplitude vibration. And then what will happen over the metal sheets? There will be huge perforation created over your workpiece surface. It will damage your workpiece surface, right? And also, ultrasonic welding is, as I was saying, this is suitable for thin sheets, thin foils, wear materials. If you were interested to join metal sheets, that should be a low yield strength material like aluminium or soft metals, zinc, aluminium, maybe copper, thin copper, not the steel metals. Of course, not the thick steel metal. Okay. Any question from ultrasonic welding?
No, sir.
Hmm. Okay. Good. Good.
Sir, sir, I want to ask a question. Sir, what is the difference between ultrasonic and welding and spot welding? And because we do in spot welding, the means the way we do welding in both are same. Then what is the difference between them?
So don't be confused. Don't be confused with ultrasonic welding and spot welding. So spot is a configuration. It can be spot. It can be seam. Now, what you are talking about, that is resistance spot welding. I think so. So what you are talking about is resistance spot welding. We call it resistance spot. It can be ultrasonic spot. It can be laser spot. It can be any kind of spot. It can be friction stir spot also. So spot is a configuration where it is only joining over a smaller area. Seam welding is an operation where you are joining over a line thing. So I mean you are joining over a length. So if you are joining like this will be your line welding. If you are joining over a small area only over a small area, this is spot welding. It differs from the power sources you are used. In resistance spot, you are using electrical resistance of the material as your heating purpose. In ultrasonic welding, you are using vibratory energy of your ultrasonic horn for your heating purpose or deformation purpose, whatever. In friction stud, that will be something else. In laser spot, that is laser. That's where we will differentiate different kinds of welding techniques.
Thank you, sir.
Yeah. Okay. So let's see if there is any question from ultrasonic, and then we'll move to friction stud. So question one is done. What about second question? The temperature generally attained during ultrasonic welding lies in the range of what? Give me some quick answer. What should be the temperature range in ultrasonic? As talked, it should not exceed your upper pure melting temperature, right? So the correct
Sir, I
answer
think
will be,
so. The answer.
sorry,
B is correct, sir.
yeah, B is correct. Right,
35 to 50%. I
of
like
the
kind
melting
of melting
temperature.
temperature.
Yes. So the temperature should be in that range in your ultrasonic welding. Now, uh, we have to state it as a true or false statement. It is mentioned that joining of two sheets in butt configuration can be easily performed using ultrasonic welding. Is it true or false? Now, in ultrasonic welding, you will have a horn tip, you will have a reflecting anvil at the bottom. Now, as you are applying vibratory energy, you need to have some
False,
amount of, sorry, tell,
false, sir.
which one is correct? True or false? This is true statement or false statement?
But configuration में this is a false.
This is false statement. Right. It's not possible to join metal sheets in butt configuration in ultrasonic welding. Mostly lap welding is done in ultrasonic welding. Right? Okay. Next, joining using ultrasonic welding methods is easiest in which of the combination? Thin sheet, low yield strength, thick sheet, low yield strength, thin, high yield, thick, high yield.
Thick sheet, low yield strength.
Is it thick sheet or thin sheet? I'm
Joining
talking about
using.
the easiest one. So if it is thin one with low
Okay.
yield strength material, that will be the best one, which will be suitable for ultrasonic welding operation. Agreed, right?
Yes, sir.
Okay. Now we'll move to friction welding. Uh, let me rub this off. Let me rub this off. So now we will be talking about friction welding. What is happening in friction welding? So over here, heat required to produce the joint will be generated by what? Some kind of mechanical friction at the interface, right? Now over here, one of your workpiece will be moving in nature and the another one will be stationary. How? So should I draw? Yeah, let me draw. Let me take some 2D figure. So let's say this is one component. This is another component. This is rotating. Okay. In the next step, what I will do, it's rotating continuously. I will apply some pressure also over here. And this is my other component, which is stationary in nature. In the next step, what will happen? I will stop my plunging. We call it plunging. When you are applying pressure in friction welding, we call it plunging action or plunging force or thrust force simply. And it is still rotating in nature. This is stationary and you have stopped the plunging. What will happen? There will be some amount of oozing out of metal in a semi-solid state. Of course, this will not go till the melting. It will not cross the melting temperature. Okay? And then you will allow it for cooling and uh, with cooling there will be sound joint which will be developed. Right? So one piece will be mounted in a some motor driven chuck or collet and it will be rotated against a stationary piece. The speed you can control. It can be as low as 800 rpm, 600 rpm. It can be as high as 2000, 3000 rpm. I personally have worked with 2000 rpm in friction stir welding. Now, with rotation, slight amount of contact pressure may be applied initially to permit uh, this oxide breakage, cleaning action, some kind of burnishing action. That will take care by the contact pressure. And then you will increase your pressure. Whenever you will increase your pressure, there will be contact friction, which will generate your heat, right? So frictional heat will be generated at tool workpiece interface, wherever you are rotating the tool due to some rubbing action of the tool, right? And as soon as you will soften or plasticize your material, it will be in some semi-solid state. Your softened metal will be squeezed out, as I was saying. So this will be something like this. It will be getting squeezed out from the interface. It will form some kind of flash. Understood?
Yes,
Now,
sir.
yeah. Now, inertia welding is a modification of friction welding where your moving piece will be attached to a rotating flywheel where the flywheel will be brought to a specified rotational speed that will be storing some predetermined amount of energy, the function of flywheel, and then it will be separated from the driving motor, right? And the rotating and stationary components are then pressed together, just the way you are doing in friction welding. So over here, what will happen? The kinetic energy of the flywheel will be converted into the frictional heat at the interface between two pieces. So this is a variant of friction welding. This is called inertia welding. Now with inertia welding, the time required to form a weld can be very short. So it can be in the order of several seconds only. Of course, this is not as small as what you see in resistance spot. In resistance spot, this is in the order of millisecond only, and also in laser spot. However, if we think of friction stir welding, inertia welding is taking very short period of time. Okay. Another variant is called linear friction welding. What will be happening in linear friction welding? The moving component over here that will be oscillating laterally. As of now, what we are saying is it will be rotating in nature. Now in linear friction, it will be simply oscillating laterally. It will be parallel to your interface, right? So it will be something like this. It will be oscillating like this, and because of frictional heating, again there will be some flash formation from the interface. Any question?
No, sir.
Sorry. Okay, so we have talked about different variants of friction welding. We have talked about linear friction welding. We have talked about inertia friction welding. Then there is something called friction stir welding. Are you familiar with friction stir welding? This technique has matured as of now in the current scenario. It is matured enough, but back in 2008 or somewhere around those years, the research was going on. This is well matured technique, friction stir welding as a solid stud welding technique. Yeah. So what is there in friction stir welding? Same, you will have some non-consumable welding tool, but over here you can have some shoulder as well as some kind of pin. It depends on what you want to achieve. So it can be a pin with pin tool, it can be pinless tool, it can be a cylindrical pin tool, it can be a tapered pin tool, it can be a threaded pin tool. There are a lot of researches have been done on this tool design, of course, and also depending on your tool dia, your the torque it will produce, right? The material that should sustain that amount of tool torque because it is rotating over your workpiece. You're getting it, right? So, as I was saying, you'll have a non-consumable, will have a non-consumable welding tool that will contain shoulder. This is called shoulder. The higher diameter cylinder is called shoulder, and the lower dia cylinder is called pin. Okay, and that will be rotating at some, as I was saying, it can be rotating at several hundred revolutions per minute, and it is then lowered, or I will be applying plunging action, or I will apply thrust load into the interface between pieces of some rigidly clamped metal sheets. So let's say I'll be having aluminium, two aluminium I want to join, and I want to do some spot welding. So I will not apply any traverse velocity. This I will not apply for a pin for a spot welding. So what I will do, I will just rotating and plunging over a specific location. So I am doing friction stir spot welding. Okay. Now frictional heat is getting generated along the top surface and also along the surface of the rotating probe. So this thing is also called rotating probe. There are some process parameters on tool design also: probe height, probe diameter. Based on these process parameters, your final heat flux will be decided, is it not? So power is basically torque into angular velocity. Okay, so torque we can include it as some torsional shear stress. This will directly depend on your, do you remember in forming, I'm not sure, this is called shear yield stress. Now if there is sliding friction or sticking friction, based on that my shear yield stress will be equal to, what is mu? Any idea? Any guess?
Coefficient of friction.
Coefficient of friction. Great. So this is coefficient of friction. This is normal
Torque.
pressure, right? And that into, what is equation for angular velocity? So how you can correlate your omega to your tool RPM? So that will be 2 pi n by 60. This is my angular speed. And P will be equal to Fn by A, the tool area, that into 2 pi n by 60. This will be my heat flux, or this will be my heat that will be getting generated because of frictional heating. So what are the parameters which are affecting your heat flux generation, which will be affecting your final temperature generation at the interface? It is depending on your tool RPM. As you are increasing your tool RPM, you will increase your final heat flux at the rubbing interface. It will depend on your thrust load. As you will be increasing your thrust load, it will be generating some higher heat flux. It will depend on tool area also. So finally, it will be depending on the normal pressure it is applying, right? Higher the area, higher will be tool torque, higher will be frictional heat generation. So those all things are interlinked. Okay, this is some numerical aspect. So I have diverted a little bit, but fine. That will be beneficial for you. Um, Now, in terms of mechanism, I was talking about this. I was talking about heat will be getting generated at the top surface, and mm, after a period of time, there will be softening or plasticization of the metal, right? It will come into some semi-solid state, and then this I was talking about spot, and if you want to do some line welding, you have to apply some traverse velocity. So for line welding operation, Traverse velocity need to be applied. This is true for any kind of joining, right? If you want to do some line heating, they have to have some welding velocity or welding speed. Question:
Sir, what is the application of friction welding?
what is the application of friction welding? So, in terms of application, there is lot of application. Whatever you are thinking of, application of fusion welding, they could be application for friction welding also. So basically, because of its solid state nature, people prefer to use this friction welding. But there is a catch, is that friction stir welding is not well matured enough to handle high yield strength materials, because you are plasticizing your material. Mostly this is widely used for low yield strength materials like aluminum, copper, these kind of metal sheets. Steel metals like nickel based metals, like they are highly what should I say, high temperature resistant materials, right? Their yield strength is much higher. Steel materials, they are not, I will not say suitable, but people do not use solid state welding as of now. This is not matured uh, enough technique for to handle these kind of metal sheets. So in terms of applications, maybe I will say, um, I will say, I will say copper aluminum joining. So for copper aluminum joining in EV, electric vehicle bus bar application. So over there, you will have some uh, battery cells. So you'll have some battery cells. Let's say this is a pouch cell. We'll have some cell terminals, and to the cell terminals, there will be some thing called bus. I'm not sure you have heard of this thing, but fine. This is called bus to carry the current. So this is one of the application. Then what else? Mm, let me think it out. Just wait. So FSW can be used in, because this is a solid state welding technique. Yeah, you can use in some aerospace structure also. So there are a lot of joining of lightweight aluminum alloys in automobiles also, right? In automobiles, lot of aluminum is used. In aerospace panels, aerospace wings, or fuel tanks, lot of aluminum is used for lightweighting purpose. You know? So there you can use your friction stir welding, as I was saying, in battery enclosure also, for automobile also, in chassis components, the automobile doors, automobile frames, they're all made of aluminum. Wherever there is aluminum, go for friction stir welding. Even nuclear fuel assemblies also, to fabricate some fuel assembly, leak proof joint. Then you have uh, for battery cooling also, So there are something called battery cooling tray. So what will be there in the tray is there will be channels produced. So let's say this is the metal where I will have some channels like this where you will flow your fluid for cooling purpose. And then what we will do, we will just friction stir weld and you will cover up that channel and you will weld over this location. You will have some CNC programming through which you can weld along the path where you have made your channel. Are you getting it?
Yes, sir.
Yeah, yeah. There are some extension of friction stir welding actually. Nowadays, you have techniques like friction stir extrusion. So all these things, what I will be talking about, is explored mostly on aluminum metals or low yield strength metals. There is this friction stir extrusion. There is friction stir deposition. Primary funda is same. So you'll have tool rotation. Because of tool rotation, there will be frictional heating. Because of frictional heating, there will be plastic deformation. So the plastic deformation will take care of what you want to achieve. If it is extrusion, extrusion will happen because of plastic deformation. If it is deposition, deposition will be happen because of plastic deformation. Then there is something called friction stir channeling. This is a little bit complicated operation in terms of friction stir. So there are some customized tool design where you will have some. I'm little bit diverting. Okay, uh, I don't know if it interest or not. Are you feeling interested? Then I will continue, or else we'll move to the other thing. So it's mostly on the research aspect I am talking about as of now. What I am mentioning. Yeah. Are you feeling interested?
Yes, sir.
Okay. So I was talking about.
Also, sir,
Yeah.
a solid state building reduce heat affected zone
Of course.
and many
So
problems of fusion
yes,
buildings.
yes, yes, yes.
Uh,
So because of its solid state nature, your heat affected zone will be less compared to the fusion welding technique. Correct. This is an advantage of solid state welding in terms of grain structures also. In fusion welding, you will have some. Let's let's go into metallurgical aspect. So in terms of grain structure, so friction stir welding is basically a high strain rate process. So your strain rate will be very high, like what happened in uh, crashing, in any kind of automobile crashing. It will be a high strain rate process, not a high strain process. You're familiar with strain and strain rate, right? In friction stir welding, your yield strength of your material will be a function of strain rate, and temperature. So in friction stir welding, because you are doing, you are stirring your material all over again and again with time, the strain rate will be very high, and because of that, there will be lot of dislocations, and because of that, there will be refined grain structure. How refined grain structure will help you? It will enhance your both strength and ductility. So these are some, what should I say, well-known aspects of metallurgy, mechanical as well. Let's not move into that direction. Okay. Yeah. Any more questions on friction stir or solid state? If not, so there is a simple numerical question over here. Let me rub
It,
this off. Yeah.
it can be calculated by 2 pi nt upon 60.
Which one?
Torque is torque
Yeah, yeah,
and
yeah.
speed are given, and we can calculate from power equal 2 pi nt upon 60. Directly sir, 2 pi nt upon 60.
Yeah, great. Power is
P
torque into omega. So it will be 2 pi nt by 60. Absolutely.
watt.
This is in watt. So I'm not doing the calculation all over again, because you know the concept as of now. So I have well explained the things. Right. So we should move on, right?
Okay, sir.
So what we will do now is diffusion.
Question number 6, sir.
Question number 6. Yeah, I will go after discussing the diffusion part. So
Uh,
there are questions from 6, 7 are from diffusion. Yeah, question 8 is from friction stir. Which of the following is not a typical advantage of friction stir welding? Which one?
not a typical advantages. Friction.
What are the advantages of friction stir welding? Whatever is mentioned over here. Of course, the energy consumption will be less because temperature is less compared to fusion welding technique, where you are using high power, high voltage, low current. So this is an advantage of friction stir because temperature is within melting temperature. This is also an advantage, minimal distortion and residual stress. So if you ask me, both B and C, high strength materials are the high yield strength materials, right? So it can be nickel based, it can be steel. You can weld. So we have done dissimilar metal welding through friction stir, like aluminium to steel. But if you want to join steel to steel, there will be lot of frictional heat source, right? To plasticize your steel material. Or if it is a nickel based alloy of some higher thickness, the frictional heating should be much higher. there is another limitation, in friction stir welding, because you are applying some plunging force, you are rotating your tool, it's all mechanically activated, right? So, uh, your friction stir welding machine should be very rigid in nature. It should sustain the vibration, whatever is happening during a joining process. So, all those machines should be heavy duty machine. That is one limitation of FSW. I will not say limitation, but yeah, that is there. And also generation of significant amount of spatter. It is not there. It is not like significant amount of spatter will not be produced in friction stir welding. Yes, some amount of flash can be generated. It can be oozed out from your metal contact interface. So B and C both. Agreed? Next for question 9, I still not have talked about this diffusion welding technique, but yes, a vacuum chamber is required in uh, diffusion welding technique. Just a minute.
Yes, diffusion, bounding,
Hmm.
ultrasonic, no need friction welding, no need submerged arc welding, no need. Only diffusion bounding.
Hmm. How about question 10? Which of the following are true for FSW process? FSW results in refined microstructure in the stud region. Yes, I mentioned that. Density of weld joint is lower than that obtained through fusion welding. Is it true or not? What
Not
is
sir.
density? Is
Option
this
C is correct.
option C is correct? Option A is also correct.
Yes, sir.
So A and C. Kumar, you agreed, right? Is there
Yes,
any
sir.
confusion? You can ask.
Yes, sir.
Yeah. Okay. Next, we'll move to this diffusion welding technique. We'll try to wrap up quickly. So for diffusion welding, there the surfaces that you want to join, those are maintained in contact under sufficient pressure. There should be some pressure and time at elevated temperature. So time, temperature, pressure. These are three main process parameters for a diffusion joining to happen, right? Over here, we'll have some clean, flat, well-prepared surface uh, under some low pressure. Of course, it should have some firm contact under some low pressure at elevated temperature. Of course, it should be within the melting temperature. There will be some kind of atomic diffusion that will provide the necessary filling of gaps, right? So if you have some surface like this, if you have some surface like this, if you apply pressure at some elevated temperature for some time, there will be something called volume diffusion, grain boundary diffusion. Not going into all detail. because of which these voids will be getting shrinked, right? So there will be void shrinkage, and in grain boundary diffusion, what will happen? There will be migration of your grain boundaries to form some metallurgical bonds, and finally it will give you some sound joint. One thing you have to remember, diffusion in solid state condition is not rapid compared to if it is happening in a liquid state. So I will talk about diffusion coefficient. So diffusion coefficient in solid is much slower than diffusion coefficient in liquid, right? This is well known. And as I was saying, diffusion bonding is performed in a vacuum or an inert gas atmosphere. So what is diffusion basically? What is
So
diffusion?
diffusion is the mixing of two fluids or two gases.
Yes, in terms of solids, in terms of solids, you can think it of as atomic diffusion. So what will happen for atoms? There will be atomic network for your metal sheets, right? Now the atoms will jump from one atomic site to other, है ना? So
like covalent bonding और अपना
yes,
मेटल बाउंडिंग्स जो इसमें होती है
there are different bondings.
ऐसे
So if you are applying some kind of uh, external application like temperature or pressure, atoms will jump from one place to other. There are different mechanisms of that. So they can jump in a random way. In terms of diffusion mechanisms, let me write it down. What different mechanisms you have come across? There is something called substitutional diffusion. Substitutional diffusion that will occur by the movement uh, of course, atoms from one atomic site to other. Now, a straightforward swapping of atoms will require a higher energy, right? So, swapping of atoms would need to physically push other atoms out of the way in order to swap places. So, if you want to swap within each other, it will require higher amount of energy, right? So, yes, one kind of substitutional diffusion is a ring diffusion. So, if you have crystals, atoms arranged in this way, this will replace over here, this will replace over here. It will be random in nature, of course, depending on your temperature, depending on your pressure. It is a direct swap method. Now, this kind of mechanism is not observed in practice. In practice, what is seen is something called vacancy diffusion, right? So substitutional diffusion in practice or in practice means in reality or what is seen experimentally by doing some analysis. Of course, substitutional diffusion occurs only if vacancy is present. What is vacancy? Vacancy is a missing atom in the lattice. So if a vacancy
It
is present,
it
one of that,
required
yeah,
less activation energy
less activation energy,
during
right? Vacancy is
bounding.
much easier to move,
Yes, sir.
right? So yeah, if vacancy is present, one of the adjacent atoms can move into the vacancy. That will create vacancy on that side, and in the same way, there is an equal probability of an atom moving into any adjacent atomic site. So if you have atoms like this, if you have vacancy over here, if you have vacancy over here, if this atom is moving towards this, it will create vacancy over here, and the next atom can move over here. It is very random. Diffusion process is very random in nature. And another diffusion mechanism is interstitial. What is interstitial?
Very small spaces left between two atoms or molecules.
So, for interstitial, the diffusing atom is not on a lattice site. So, wherever there is presence of atoms, we call it lattice site. And in between these spaces, these vacant spaces, these are called interstitials. So, the diffusing atoms is not on a lattice site but on an interstices. So, to occupy that space, the interstitial atom that must be of lower dia. The atomic radius should be lower in nature, right? Otherwise, how your interstitial will happen? I know. So, yeah. Now, the rate of diffusion is controlled by the ease with which a diffusing atom can move into an interstice, right? So, these are three mechanisms of diffusion for diffusion. Now, if we talk about different I would say different theories of diffusion, how you can define a diffusion flux, or what should be the diffusion flux uh, with which the diffusion will be easier. What parameters does it depend on? It depends on, you have heard of Fick's law of diffusion, right? Sorry. You have heard of Fick's law of diffusion. What does it say? Your diffusion flux is equal to diffusion coefficient, and that is proportional to your concentration gradient. Higher the concentration gradient, faster will be the diffusion. Higher the diffusion coefficient, faster will be the diffusion, right?
Yes, sir.
Okay, so let's not go into much detail. Uh, yeah, we'll do this. We'll answer this question and we'll wrap up over here. Maximum activation energy is required to cause. Which one is required? Maximum activation energy.
I think exchange diffusion and ring diffusion from between two. One is correct.
So exchange and ring is almost same kind of thing. So wherever there will be exchange of atoms, it will have higher activation energy. Vacancy diffusion is having lowest activation energy.
Yes,
Next, I have asked diffusion flux in a diffusion process depends on which factors. One more thing is, so I have talked
all
about
of
diffusion flux. Yeah.
all
So
of the
all of this. Yeah. So this diffusion flux depends on your diffusion coefficient, concentration gradient, and how your diffusion coefficient will vary with temperature. Is there any equation through which you can state that yes, this is my diffusion coefficient at this temperature? There is something called Arrhenius law. So Arrhenius law will tell you how your diffusion coefficient will be varying with temperature. So over here, let's not go into detail, just to have to give you some glimpse of how the works happen in diffusion. So Q is activation energy of that atom, R is universal gas constant, and T is temperature. So over here, higher the temperature, higher will be diffusion coefficient, faster will be diffusion, right? All of this, yeah. So we have done 7, 8, 9, yeah. It's all done,
yes, sir.
great. Any question till now?
Sir, what is the meaning of EXP in the formula?
What is the meaning of
EXP,
EXP?
denote
This is
EXP.
exponential. So this is exponential. So this is an exponential function. So G naught into e to the power, that should be minus e to the power minus q by RT. This is an exponential function. So with increase in temperature, your diffusion will be exponentially increasing. That's what Arrhenius states. Okay. Anything else? Thank you. So we'll finish it off today. We'll meet again next week.
Yes, sir.
Have a good day. Bye bye.
Okay, sir. Thank you, sir.
Thank you.
Thank you, sir.